All right, continuing on where we left off. So question 5, the group 7A elements are called the, let's take a look at the periodic table, and those are the halogens. Okay, remember in group 1A is the alkali metals, 2A is the alkaline earth metals, 7A is the halogens, and the next question is, the group 8A elements are called the, the transition metals. That's the big block in the middle. The alkaline earth metals, that's group 2A. The alkali metals is 1A. We just did the halogens, so that leaves the noble gases. So which region of is groups 3 through 12 on the periodic table? That's this section in the middle here of the periodic table. So group 1 is the alkali metals, 2 is the earth metals, 7 or 17 is the halogens, 8 or 18 is the noble gases. There is no particular category for the rare earth metals, so that leaves the transition metals. Okay, so based on its location in the periodic table, which element has properties most similar to calcium? So I'm going to scroll down. I've got a periodic table here. Now remember that everything in the same vertical column will have similar characteristics. So here's calcium right here, element 20, and we want to pick something that is in the same vertical column as calcium. So potassium is in the first column, magnesium is in the same column as calcium, scandium, SC, let's see, where does SC live? Oh, SC is in column 3. Bromine is over on the far side of the table, element 35. And cerium, Ce, let's see, where does he live? Or she? Oh, cerium's way down here in the lanthanides. So we're going to pick magnesium because it's in the same column, the same group as calcium. So which of these does not react with the other elements? So remember, the ones that don't react with other elements, those are the noble gases. All right, so let's take a look at a periodic table and find the noble gases. That's right over here on the right in group 8. So helium, neon, argon, krypton, xenon, and radon. That means neon is our choice. So which pair of elements has the most similar properties? So let's take a look. So hydrogen and neon. So hydrogen's over here, and neon's on the far side of the table. Okay, we're going to be looking for something that has going to be in the same vertical column. What's our next choices? Uranium or neptunium? So uranium is way down here, and neptunium is to the right of it, but we want things that are in the same vertical columns. So argon and krypton, that's our third one, Ar and Kr. So here's argon on the right, and krypton is right below it in the same vertical column. Let's see, titanium or tantalum, T-I or T-L. Let's see, here's TL, element 81, and titanium's way over here, so nowhere near each other on the periodic table. And then lithium and beryllium, Li and Be. So lithium is here, beryllium is right next to it. We want things in the same vertical columns. That means that argon and krypton are going to be our most similar. All right, so uncovering atomic structure. So we talked earlier in the previous video about Dalton and his atomic theory. And at the time, they just knew about atoms. They knew that matter was made up of a small, indivisible unit of matter. But they didn't have any concept of the idea that the atom itself was made up of smaller parts. Right, so we have here, this is Dalton's atomic theory. And what they did was they were, around the 1800s or so, they started to develop ways to uncover the different parts of the atom. Okay, so here we have the discovery of the electron in 1897, and that was done using a thing called a cathode ray tube. Okay. And the image that we have here on the right is the very first actual battery, and it was invented by an Italian scientist named Volta, which is why we have units of electricity are called volts. It's named after Volta. And in this image, we have a stack. This is actually called Volta's stack. And it's a stack of alternating copper and zinc plates. And in between each of those plates is a very thin piece of fabric that's been soaked in acid. Okay, and by stacking up all these plates, it creates an electric voltage. And then a little bit later, in 1897, they discovered electrons by using a particle source directed at a target that would sense it when it hit. And when they put a positively charged plate here above that beam, it made the beam deflect. It actually attracted the particles in that beam. And so they were able to figure out that those were actually negatively charged electrons, because positives and negatives attract. Then in the early 1900s, they have what's called the plum pudding model. And in the plum pudding model, they envisioned that atoms were just spheres of positive charge. Okay, with little particles, they knew about electrons at this point in time, with little particles of electrons floating around in that charge. Okay, so they had no idea that there was anything solid inside of an atom. So in 1909, the famous gold foil experiment was conducted. And what they thought was going to happen, if they were basing things on the plum pudding model, is that if they fired an alpha particle, which is basically a helium nucleus, if they fired an alpha particle at an atom, it should pass right through, just like it does right here in the top of this image. But what they found instead was that some of those alpha particles get deflected, like it does here, or bounce back, like it does here. So if the plum pudding model was correct, they couldn't explain this behavior. But if there was something solid inside of an atom, then it could explain why the particles were being deflected. And so they came up with the idea of a nucleus. And what they decided was that most of the mass and all of the positive charge was located in the nucleus. Okay, so you have protons with positive charge. And then to balance those, to go along with those protons, they also figured out that there were neutrons. And notice that the mass of a proton and the mass of a neutron are very close to each other. Right? And the neutrons have no charge whatsoever. They are electrically neutral. And then flying around the nucleus, you have an electron cloud, and all of the electrons are negatively charged. Okay, so protons are positive, P for positive, P for proton, and electrons are negative. Okay, so if I have, and most, or if not all atoms are electrically neutral in their natural state. So that means we have the same number of electrons as we do neutrons. Same number of positive charges as negative charges, so that we end up with no electrical charge. They cancel each other out. So which particle is not located in the nucleus? So if the nucleus is made up of protons and neutrons, then the only one of these three that is not it's not part of the nucleus is the electron. So which particle has an overall positive charge? So P for positive, P for proton. All right, now the other thing that I'd like to point out at this point in time is that the mass of a proton is about 1 mass unit. Okay, and we're going to talk about different types of mass units, different measurements of mass as it pertains to the teeny, 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 infinitesimally small particles of inside atoms. But a proton has approximately 1 mass unit, and a neutron has approximately 1 mass unit. So if I have a nucleus that has 1 proton and 1 neutron, that atom is going to be very close to 2 mass units. Okay? Because the electrons are super, super light, very, very small. Now the protons, the number of protons determines the identity of atoms. Okay? Identity of atoms is related to the number of protons. So if you look at a periodic table, every single element has a different number associated with it. Carbon is 6, nitrogen is 7, oxygen is 8, fluorine is 9. That is the number of protons. Okay, so the atomic number, that big number that you see in every periodic table with an element, is the number of protons. Okay, the atomic number. All right, now the mass number is the number of protons plus the number of neutrons. Okay, so if I have a mass number of, let's say, 12, and I'm talking about carbon, if I know that it's carbon, then I know that it has 6 protons. So if the mass number of 12, 6 of those are protons, that means that the rest of them, the other 6, are neutrons. Now, isotopes have the same number of protons as any other atom of a particular element, but has differing number of neutrons. And we'll talk about that in a little bit more here in a minute. So the periodic table usually shows the atomic number and the average atomic mass. That's usually this number down here. Right? And there are a couple of ways that we symbolize elements. So this big HE with the mass number, atomic number, that's one way that we go about it. So if I were to do HE and put in the numbers, this would look like HE, and the atomic number is the number of protons, so that's 2. And the number of neutrons is also 2, so the mass number will be 4. Okay? So another way to show that would be to simply put the symbol, a dash, and the mass number. So using this helium example, I would write this also as helium-4. Okay, so I'm going to go ahead and stop this video, and we will return with number 13.